Assalamu alaikum. In this recorded lecture, I will be explaining the modal analysis for this problem, which has been clipped from the question paper of midterm exam for the session 2020, subject mechanical vibration. And this problem was actually a bit modified from this example 2.1, the harmonic response of a water tank. Uh, so this is the actual physical diagram for this problem. Here, this is the water tank and this is the column. And this is the FBD, which is showing its lateral vibration or oscillation. This is the its response, which is shown by XT. So, first of all, we will be requiring some calculations. As here we can observe from the statement that the length of the column is 100 meter and the Young's modulus value is this 30 gigapascal and inner and outer diameter, because this is a hollow section, uh, tubular section, and the frequency for the tank is 2 hertz lateral frequency, and we will be calculating its mass and other necessary data. And for this, we can observe some calculation here, that this is the outer diameter and this is the inner diameter given, and the formula for calculating second moment of area is this, and this comes out to be 2.0586 meter raised power 4, and then stiffness has been calculated inputting the data, and this comes out to be 1.85, and after that mass has been calculated like this. This is 1171.5 kilogram, and if we account for the effect of the mass of the column, this is the end mass of water tank, and if we add the mass of the column, so it's 33 by 140 factor is added in the mass of water tank plus water, and its new frequency comes out to be 1.906, approximately 1.9 hertz. So, and this is the schematic diagram in this way. So to create this problem, what we will be doing, that we will be starting a fresh new project schematic, and then we will be clicking on this module, and then we will be left pressing and release the cursor in the screen here in create standalone system. When we are in this box, we will be releasing the left mouse button, and here the module will be shown here, and then we will be launching design modeler geometry module, and geometry module has been loaded, and after that we will be creating this schematic model for the cantilever beam representing the mass of the column. And as the column is in the vertical orientation, so we can better draw it along the vertical axis. To start it, we will simply click on XY plane, and as shown, the XY plane has been selected and shown, and after that we will be bringing it into planar view. So for this, we can click on this look at face or plane or sketch icon, or alternatively we will simply be clicking on this z-axis when it has been highlighted. So we can either click on this z-axis, or in other situation we can click on look at face or plane icon in this way. So after that, we will click on sketching tab and click on line, and then we will be starting from the origin. We can actually start at any location, but I will be starting from the origin. And as soon as I bring the cursor near the origin, I observe that capital P constant has been shown, and this means point constraint. And as I bring on the cursor on the axis, it is showing C constraint means coincident constants. And here at the origin, as origin is a point, so it is showing point constant. I will be starting from this point. I have clicked it here and placed the random length of representing the column along vertical axis, and after that I will be placing a random general dimension here. And as I have finished this dimensioning, here parameter v1 is showing, and in the details view of the dimension here v1 has been shown. So we will be clicking on it, and as we observe from the statement of the problem that the mass and the length of the column is 100 units, as we can observe here 100-meter high column. So put here 100, and then as we can observe that and the sketch has been created, and after that we will be clicking on modeling tab, and after that we will be going to as we can observe that in the XY plane is showing this plus icon. We will be clicking on this plus icon and expanding it, and we will be selecting this sketch one, and we will go to concept menu, and here we will be creating a line body. To create a line body, go to concept and click on lines from sketching, and here as the sketch was already selected, so click on apply and generate it. And as we observe here, one part one body, and it means one line body has been created. And in the details of the line body, we observe that the cross section is missing. So now we will be defining the cross section. This is very, very important. Cross section, here we observe there are different cross sections, but we will be observing the circular tube because the water column is actually a hollow tube having inner and outer diameter as shown in the problem statement. This is the inner diameter 2.5 meter and outer diameter 3 meter. So we will be inputting here the data, concept menu, cross section, and then circular tube. And here we observe that, remember, we will only be inputting data here. We cannot input data for this inner and outer radius or diameter in the graphic screen. So here we will first of all be defining its outer diameter, and outer diameter is 3 by 2 means 1.5, and the inner diameter was 1.25, so its radius will be was 2.5, so its radius will be 1.25. So as we observe that this has been defined. After that we will click on line body, and here from the menu we can select circular tube, and in this way. And after that, to visualize in 3D solid body, we can indicate, we can click, we can check out this cross section solids. And as we observe that here the column has been created, and after that we can click on this display plane, and we observe that we can zoom in this portion and observe, as we can observe that inner portion is hollow, and this is the inner diameter and this is the outer diameter. So in this way this ring has been generated, and hence the modeling part for the column has been completed. And after that we will be finishing it. After we can observe here some details in the line body, and because it actually line body. No necessary details are shown here. After that, we will be clicking on this model cell. We will be waiting to start this model cell A4 starting as mechanical. As we observe that model has been highlighted and loaded, and we can show here cross-section solids or geometry, and as we can obs observe again that this is the hollow tube has been shown, and after that we will be clicking on geometry and expanding this line body and go into its details. Here in the bounding box we observe that this length along y is showing 100 meter, and as we observe that length along x and z axis is 0 as the column was placed along vertical axis. And into the properties we observe that this is the volume for the column and this is the mass, and as we observe that the default mass is sufficiently large, we have to make this column massless because we will only be checking the effect of this end mass, water tank and water. So we will be actually making this column as a massless so that its effect is not accounted for in the first case. So to do this, what we will be doing, we will be going to clicking on this engineering data, and in the engineering data we will be changing its density to be, for example, E minus 40 minus 40 and 1E minus 40. That means the density is very small. So after that we will be clicking on this model cell A4 and refresh materials, and again observe the properties of this line body, and here it is shown minus 38 10 raised power 38. That means a very small value, so it has been made massless approximately. And after that what we will be doing, that we will be changing its analysis setting here, maximum mode to find here is written 6, we will be changing it to 1 as this is a 1 DUF problem, so only one mode is required. And furthermore we will be adding its end mass. End mass is, we will be clicking on geometry, right click and go to insert and then click on point mass, and here we will be uh, applying the end mass at this topmost point. We will be clicking on this point or vertex filter, and here this point filter, and click on it and then click on apply, and here we will be inputting the mass of the water tank plus water, and it was calculated in our problem. As we can observe here that it was 1171.5 kg. So we will be inputting this mass here 1171.5 kg, 1171.5 kg, and after that we will go on this model A5 cell, and we will be applying necessary loads and constraints. So here we will first of all be making its lower end base point as the fixed support, and because the base of the column has been fixed with ground, and after that we will be clicking on insert and go to displacement to define its DOF in the XY plane. As we can observe, the upper end or the topmost end where water tank has been located, and this is confined to deflect in the XY plane along x-axis only. So we will be clicking on this point and we will be making it free in the x direction because it will be deflected in the x orientation. So we will be clicking on y component to be 0 and z component also to be 0, and only x component will be free. So as the column is along vertical, so its deflection is possible along x-axis only. So necessary loads and supports have been applied, and after that we will be clicking on solution, insert, and deformation and total deformation. One important step before solving is that in our problem statement, uh, here the Young's modulus value is 30 GPa, means 30 gigapascal. So we must change its modulus of viscosity value. We here default value is 2 10 raised power 11. We will be changing it to be 30 E9, mean 30 gigapascal. So as we can observe, so this is the Young's modulus value. Again, we will be refreshing the materials here. Click on model cell A4 and click on refresh materials. And then now we will be observing, we will be solving this problem and wait for the solution. And as we can observe, here the frequency is shown 1.998 hertz. So which is almost 99% equal to the exact value which is required. Hence, it has been verified that our given frequency is satisfied. And after that, our next task will be adding the effect of the mass of the column. So what we will be doing, that we will be launching a new module, and as we observe that uh, the geometry is same, so we can interlink the geometry, and furthermore the mass of the column also is massless because its factor will be added in the end mass. So we can also link the engineering data. So after that we will be clicking on this model cell B4, Uh, Here again, we will be checking this line body properties here. And as we can observe, the same properties as the data has also been shared. So after that, we will be inputting this. We will be clicking on right clicking on geometry insert and point mass. And here the point mass will be equal to the sum of the two masses. Sum of the two masses, which is the mass of the column, which will be added into this end mass, which is the mass of the water tank plus water. So there are two ways to add this mass. One is that we can add two individual masses like this. For example, this is point mass for the uh, just water tank plus water, which was 1171.5, and this point, click on point filter and then click on here, and this point mass we can also rename, for example, it uh, water tank plus water mass in this way. And after that, we can add another point mass here at the same location, and this point mass will actually be, if we rename it, this point mass will be the mass of the column. We can also name it effective mass, effective mass of column. So what will be the effective mass of column? Here we can observe in the calculations that the actual mass of the column is, total mass is 500 kilogram, but its contribution in the frequency is the factor 33 m by 140. So if m is the mass of the column, then it's only 33 by 140 factor should be added into the end mass or mass of the water tank plus water to account for the frequency. And remember that this 33 m by 140 is the factor in the case of cantilever beam. If they are simply supported or some other type of beam, then some other factor will be calculated. So remember it. And what we can do here, that now we can add this value is actually, here it is shown that this end mass which can be shown here, this can be calculated, and here we can calculate this mass. The mass of the mass of the column was 500, and we will be multiplying it by 33 and dividing it by 140. So this, the 33 by 140 factor is 117.85. So we will be adding this factor here. So 117.85 117.8571. 117.8571, and we will be clicking on the same point. So both meshes are added at the same point. After that same, we will be inserting fixed support at the lower portion, and after that we will be clicking on the displacement support. Here we will be applying the displacement constant so that the deflection is only along x-axis, because we assume that the wind or gale is along x-axis, the beam or the column is in the vertical orientation, so the deflection is along x-axis. So x is free and y is 0 and z is also 0, and also highlight this point and click on apply. And in this way, after that insert, then click on deformation, total deformation, and observe its new frequency to solve it. As we can observe here, the new frequency comes out to be 1.9045, and our theoretical calculation was 1.906, which is approximately equal. So in this way, this case has also been satisfied and verified. And remember here, we have added 2-point meshes, one water tank plus water mesh individually and an effective mesh of the column. Remember that we can add only a single point mesh, and we can simply add these two meshes numerically, and we can input here only one mesh, point mesh also. Uh, so in this way, it has been calculated. Another possibility and verification to account for the effect of the mass of the column can be such that we will be adding another modal module, and here we will be clicking interlinking the geometry is same, so the geometry has been interlinked, but we will not be interlinking the Yang data. We will actually be now uh, calculating the density for the mass of the column. We will actually be calculating the density for the mass of the column. We will be calculating the density for the mass of the column. So in this technique, what we can do that we will first click on this model cell C4. As the model has been highlighted, and in a similar manner, what we will be doing, uh, we will first of all be checking the properties of the line body here, and here in its properties, as we can observe that its volume is 215.97 meter cube and its mass is given this value. So we will be calculating its new density, and new density will be, as the mass of the column is physical mass was 500 kilogram, so we will be dividing the mass of the column over this volume and we will be obtaining new density. So that mass here obtained is 500 kilogram. So what we can do, that we will be calculating new density. So to calculate the new density, we will be dividing this mass of the column over uh, this volume 215.97. So 215.97. So 217.95, and here we observe that the value is 2.2941. So 215.97, sorry. So here the value was actually, we were required to divide 500 over 215.97. So here it comes out to be 2.3151. So we will be inputting its new density here in the engineering data, and new density is uh, 2.3151. And again here the Young's modulus will be its value 30 gigapascal, which is equal to 30 10 raised power 9. So again this refresh the materials and observe that new density must be picked up, and here verify that here mass has been shown 500 kilogram, and in this way. So in this way mass of the column has been distributed, and now we will be clicking on insert and add the point mass, and here we will only be inputting this point mass, which we can rename it water tank plus water, and we will be selecting this upper point, and here we will be adding the same as 1171.5 kg, and because the mass of the column is now distributed, and now we will clicking on insert, and we will be adding a fixed support at the lower end, and after that we will be clicking on displacement support here at the mm, water tank point. We will be clicking on apply and expiry and z0, y is y and z both are 0. So also in the analysis setting, put its mode to be unity as a 1D problem, and then we will clicking on insert and deformation and total deformation here, and in this way now we will be solving and checking what is the answer. As we can observe here, that the same answer approximately has been obtained 1.9042. So in this way, we have observed that if the actual mass of the column, distributed mass of the column is used, then also there isn't any change in the frequency and hence it has been satisfied. So in this way, this problem has been completely satisfied and solved. And thanks all for listening. Assalamu alaikum.